So moving on, you just have to remember to regard when we are dealing with an S&2 reaction, the trend of the nucleophile can be different as when we are dealing with protic or aprotic solvent, such as this one. Okay, the trend of the nucleophiles, and of course the vicissitude. The nucleophiles will be different when we have a different environment. So again, the extent of hydrogen bonding with nucleophile varies with the identity of the nucleophile. So hydrogen bonding with the small nucleophilic atoms is stronger than larger nucleophilic atoms. I have already explained that earlier. Solvation is much effective when we are dealing with a small atom than a large atom. So what happens when we have in protic solvents now with nucleophiles having different atoms involved? So the greater reactivity of the nucleophiles with large nucleophilic atoms is not entirely related to solvation. We've learned earlier that the larger the atom is, the lesser will be the solvation effect. So because there is a lesser solvation effect in the presence, you have to mention the presence of the protic solvent. No? So it becomes more available to attack the substrate. Okay, but sometimes nucleophilic atom, the size of the nucleophilic atom is not entirely related to solvation. Larger atoms have greater polarizability. I have mentioned that earlier. So there are two factors that can be considered, no, when we're talking of the nucleophilicity of an atom, of a nucleophile, no. So larger atoms have greater polarizability, and therefore larger nucleophilic atoms can donate a greater degree of electron density to the substrate than a smaller nucleophile. Okay, so aside from that, aside from the one that we mentioned, that the greater, the larger rather the atom would be, the lesser will be the solvation effect. No, so because there is a lesser solvation effect, then the nucleophile will be more available as compared when we are dealing with a smaller atom. There is a greater solvation effect. There is greater solvation. The nucleophile are readily stabilized, no, by the solvent, by what you call a solvation effect. So there is less availability. But other than the size of the atom, solvation effects of the atom based on the size, there is another reason that the larger atoms will become more nucleophilic than the smaller atoms. And the reason is polarizability. The larger the atom, the greater is its polarizability, meaning that its electron density can be easily distorted. No? Mas dako siyang area for which the electron density can be moved or can be distorted. And because of that, there is a larger polarizability of the atom. Therefore, that certain atom, that certain nucleophile, that large nucleophile can easily donate in a greater degree for its electron density to the substrate as compared when we are having a smaller nucleophile. So two things to consider when we're looking at the size. For larger atoms, there is lesser solubility or rather solvent effects. Again, we're talking here of protic solvents. And secondly, that larger atoms have greater polarizability and therefore it has more tendency to donate its electron density paingon kang substrate. So two things. You have to take down notes for that. So in effect, now we can, here is the list of nucleophiles in protic solvents. You have HS, NC, IOH, and 3BR. Okay, so you will check on the size here. Sa HS, CN, iodide, OH, N3, BR, CH3, so CLF. Okay, just have to somehow, if you couldn't memorize, just familiarize with it. No? So you notice that if you are only dealing with a similar group, no, it's easy. But when you are dealing with different atoms, it can be quite complex. So let's see, sulfur and iodine. Si Ronald kay 70 Adventist. Okay, what's the name? So, periodic table, I forget. Do you have questions? I just go back to ko ba sabi? So for an iodine, yes, you can compare HS and iodine. Of course, iodine is much larger than sulfur, no? But we noticed here that HS is more nucleophilic than iodine. Of course, okay, so you just have to memorize on this trend here. HS, HCN, iodide is more nucleophilic than OH, no? Iodide is much larger than OH. And the N3, of course. You have to remember this one is the most nucleophilic, the HS. Two reasons. Nice. If you compare it with HS and OH, of course, you readily know that HS will become more nucleophilic than OH by virtue of sulfur, more larger than OH, CHS minus OH. No? And iodine is much more larger than OH. Now I was looking at checking on the anyway, so this is the trend. You have your HS to be more nucleophilic than CN, and you can HS and CN now the orbital, hybrid orbitals, it's also being utilized. Can also be a factor, but sp3, yeah, S3, sp3, it's using the sp3, so it's more polarizable than HS. You have a greater P character here. So you just have to memorize on the trend. If you are dealing with same group of atoms, no, like same family, same group rather, no, HSOH can be easily to memorize. Iodine, bromide, ClF, no. But when you are dealing with complex different atoms, simply you just have to memorize on this. So let's consider the solvent effects in SN1 reaction. So earlier I mentioned that polar protic solvents favors, before I forget, like always have to remember when we are talking of the nucleophilicity, we have to consider whether we are handling the nucleophilicity in terms uh, of the environment, no? So is a nucleophile placed in a protic or aprotic solvent, because it will matter. So now let's move on to the effect of the solvents to the SN1 reaction. So earlier I mentioned the SN1 reaction. In the SN1 reaction, the use of polar solvents, polar protic solvents actually favors the SN1 reaction. And a protic solvent, protic has at least one hydrogen atom. So protic from the word proton, no? You have your protic solvent. So again, you'll be using water, ethanol, methanol, and similar species, similar substance. So let's say here, in a protic solvent, so this one hydrogen bond. So what is the role of the solvent, of the protic solvent in the SN1 reaction? Again, we have to remember on the mechanism of the SN1 reaction in the first step of the SN1 reaction. It will always involve, again, the formation, we'll have to emphasize again, the formation of the carbocation before the nucleophile attacks. So whatever can stabilize your carbocation and your living group, no, it will promote on the formation of the carbocation or stabilize to form the SN reaction. Okay, so the first step is the living group leaving the substrate. So how can this living group be stabilized? It can be stabilized by interactions with the waters. For example, chlorine will have a hydrogen bond interaction or hydrogen bond interaction with the solvent, no? And when it leaves, so there is this partial formation of hydrogen bond with the living group and the hydrogen. So there is that here, which means that there is interaction via hydrogen bond. So because of that interaction, the living group would have more ability to leave the substrate because it's being stabilized by the solvent. So when the living group leaves the substrate, there is this developing of a partial negative charge. When the living group leaves, it will carry with itself the partial negative charge and would leave carbon the partial positive charge. Okay, so mag-develop a partial positive charge and mag-develop a partial negative charge on the chlorine and a partial positive charge on the carbon. But on the side of the chlorine, which is our living group, the developing or the chlorine group, having developed the partial negative charge, can be stabilized by the H2O, the solvent, okay? Such that when it fully leaves the substrate to form the intermediate product, no? And this is again the transition state. Transition state is temporary siya nga structure or formation before you get your product. But again, since this is our elementary steps, no, we don't actually get the full product, but the product that we get initially is the intermediate because this is not yet the full product of the reaction here. We're just talking about the step 1 of the SN1 reaction. So in the formation of the carbocation, no, when the living group totally leaves the carbocation, it can be stabilized by the solvent, by again solvation. But how does the solvation occurs? By again hydrogen bond formation. And because of that, no, so di lang siya kay lakas loob siya mobiya, no, kay siya lang. There should be a way, because of course it will develop a negative charge. There should be a way where the negative charge that chlorine or the living group carries with it can be stabilized. No, there will always be a counter ion nga mo partner sa iyaha. So the only system that can stabilize the negative charge promoted or developed by the living group is due to the solvation effects by the solvent. So to be stabilized, there should be a protic solvent, and the protic solvent will undergo hydrogen bond formation with the living group. Okay, so, and because of that, it will prevent the living group to interact again with the carbocation. Again, what are the protic solvents? Water, ethanol, methanol, and so on. And again, it facilitates the formation of carbocation kaning sa transition state. Kaning na bracket here. It facilitates the formation of the carbocation. So, a rough indication of solvent's polarity is a quantity a polar protic solvent. So how do you know it's polar? The solvent is polar or not. So an indication that the solvent is polar by looking at its dielectric constant. What is the dielectric constant? The dielectric constant is a measure of the solvent's ability to insulate opposite charges or separate ions from each other. So pag na siya ability nga mo, unsa man ang mo measure to insulate, kana bang mo assist, no, mo assist on the opposite charges the ions mo assists the ions from interacting with each other. So example, parsan ni, no? Itong dimethylformamide. For example, no, so may dimethylformamide, okay, water formic acid, no. So water and formic acid, they have dimethylformamide, it's aprotic, no. It has a strong dielectric constant, is 49. So na siya ability to insulate the developed charge having opposite charges, separate ions. Pero sa like dimethylformamide, DMF, HMPA, no, acetonitrile, no, they can only disperse the charge of the ions kani siya for the cations. For the for the aprotic solvents, they can disperse the charge of the anions, no, because of the protons nga present sa iya. So example, water, formic acid, methanol. Here, no, the protons ang iyang ma-disperse nga charge ang negative ions. Just like such as those katong sa living group. So the most effective solvent actually for promoting ionization is water. Next is formic acid. So it's siya talaga ng uban. But you just have to remember the protic and the difference in the protic and the protic solvent. For protic, it's easy to remember water, methanol, ethanol, or even the acid, no, it's still considered to be protic. Kaya na siya proton, H. So H3COH. Na katong mga acid, na siya proton. Aprotic katong walay proton sa iyang structure that can be easily ionized. Okay? Mo na to. Kumana ba ta? So I would like you to practice problems. There's answer to here and just study this one and apply the one that we've discussed earlier. Practice 6.13, 14, 15, 16. Okay, practice by yourself, 17. Okay, now let's talk on the nature of the lip. So again, I would like you to study those problems na wala na ako nakan, but there is already an answer, so you can easily analyze and think for the answer is given. So another consideration when we try to compare on the ethanol and center reaction, first the substrate, second we talk about the nucleophile, third we talk about the solvent. And the fourth, we talk about the nature of the living group. So the living group departs to the electron pair that was used to bond them to substrate. Of course, it's a heterolytic cleavage of the living group. Heterolytic meaning it takes with it all the electrons from the bond. For the best living groups are those that become either a relatively stable anion. Oh my God, it's a stable anion or a neutral molecule when they depart. Okay. The best living group, I will have to emphasize this one. The best living groups are those that become either a relatively stable anion or a neutral molecule when they depart. So and that's why we'll see later, that for OH to be a good living group, it has to be protonated first. So that when it leaves the substrate, it becomes a neutral molecule. So the best living groups pag neutral siya when it leaves or stable siyang anion. So again, how can the anion be stabilized? An ion can be stabilized by the anions. That's ions from the living groups that can be stabilized by, of course, the solvent, but another one by the nature of the anion itself, that's being formed. There are anions that more stable than the other. For example, when we talk of, say, OH and SH, right? So sulfur is much larger than oxygen, so it's larger. So as an anion, it can be easily polarizable. It's easily polarized, being a larger atom, and therefore, as an anion, it is more stable than the smaller ones. So larger anions are more stable than smaller anions. Of course, another one is resonance structure. Whenever you have a resonance structure as an anion, it can easily be stabilized. So first, let's consider living groups that have become anions when they separate from the substrates, because weak bases stabilize a negative charge effectively. Living groups that become weak bases are good living groups. The weak bases. So this is what they mean weak bases. They have less tendency to donate an electron pair. They have less tendency to donate an electron pair. And because of that, they become good living groups. I hope that, I don't know if you get my point. Weak bases. Remember, you just have to go back to the definition of the base, no? Bases are substances that donates electrons to the acid, not to the positive center, to the acid, to the Lewis acid, to the one that accepts electrons. So when they have less tendency to donate electrons, then they are considered to be weak bases. So living groups that becomes weak bases are good living groups because na naman, they are weak bases are more stable actually than strong bases. They can be more easily stabilized. When they are stabilized, for example, C double bond OO, no, RC double bond OO, they form anions, okay? But because of the resonance structure, they have less tendency to donate electrons, therefore they are considered to be weak bases compared to the OR lang, okay, RO, OR. And so therefore you can say that weak bases are good living groups and weak bases, ano to? Ano sa paman? Palit na to. Hapit na ta, gamay na lang. Okay, so let's just wrap this up. Okay, gutom na, no? Saan ako? Okay, the reason for stabilization of the negative charge is important. The reason that stabilization of the negative charge is important can be understood by considering the structure of the transition state. So again, let's consider in the SN1 reaction of when it leaves, when the living group leaves the substrate. So when it leaves, of course, it can be assisted by the solvent, no, like protic solvents. And so there is the developing partial negative charge of the living group and a developing partial positive charge on the carbon, okay? And so you see a broken line here. It means it's the bond breaking process is developing, and the living group will take with it all the electrons that is due to the bond between carbon and the living group. No? So when it leaves, you will have your positive, the carbocation, and of course your living group here. So the reason that substitution of the negative charge is important can be reasoned. Okay, you have here. So however, your anion can be stabilized here. Then you will have formation of a weak base here. So in the SN1 reaction, so where will be your living group will leave first to form that one, and in the SN2 reaction, there is a simultaneous formation again of the nucleophile, and for the living group to leave at the same time the nucleophile attack. So there is this transition state, nucleophilic backside attack to the substrate, and there's also developing like partial negative charge on the living group before it forms a full negative ion here. So stabilization of the how you can stabilize the living group during the transition states will lead to the development or stabilization of the negative charge at the living group. So stabilization of the developing negative charge at the living group stabilizes the transition state, and therefore that lowers the free energy of activation and increases the rate of the reaction. So in saan pag whatever factors that could stabilize your living group here in the transition state would lead to a lower activation energy, free activation energy in the formation of the transition state. And because of that, pag low ang free energy of activation, then it's easy for the reactants to climb the transition energy and to form the product. And when there is a low free of activation, katabi tang sa energy diagram, pag very low lang siya with respect to the product, then the reaction will be very fast. There is less energy that the reactants will need to overcome in order to form the product. Katong sa energy diagram bitaw nga katong peak no, of the curve, pag the difference in the free energy of the reactant and the transition state is not much, there's not much difference in their free energy, it's easy for the reactant to overcome that free energy of the activation, free energy of activation, or to form the product. So the trend among the halogens, an iodide ion is the best living group. Anong best living group na? Of course, the ion, when this is the living group attached to your substrate, when it becomes an anion, the iodide is more stable, being a large atom as compared to the fluoride ion. Okay, so if you have this one, no, CX, you have your iodide bromide, fluoride, no? The best living group among this is the iodide. Nga naman, once it forms the anion, okay, the living group, the iodide is much more stable than the fluoride. Again, for reasons that iodide is a larger atom than your fluoride, and this iodide can be more easily stabilized by virtue of polarization. So the electron density can easily be distorted, okay, because it's a large atom. There is much space for which the electron density of this, the developed negative charge in this ion can be dispersed because of a larger electron densities compared naman sa small atom. So in a protic solvent, however, no, the basicity, aprotic, meaning there is no proton. There is no proton. So when we're dealing with DMFO, DMSO, DMF, no. So when you are using that kind of solvent, the basicity is different. The order of the living group, stability of the living group, no, is different. So fluoride is a good living group as compared to chloride, as compared to bromide, as compared to iodide. Why is that? Why is that? No, so this one is can be stabilized. Now, what is the so this one, in this case, the fluoride ions here have you can look at on this transition state, no, it can easily leave in the SN2 kind of reaction when we're dealing with a protic solvent, no. For the living group to easily leave this transition state, no, it has to be smaller as compared to this one. Okay, so the larger manggod, your ion, no, it's hard for the nucleophile to attack, no, pag large siya. So therefore, the nucleophile cannot easily attack your substrate. So in this case, that's why running out of time. So 10 minutes. In this case, when we're dealing with SN2 reaction, again, here, dealing with SN2 reaction, we're dealing with aprotic solvent. Usually we're using aprotic solvent. So here, when the substrate, when the living group is smaller here, then the nucleophile can easily attack. Now, there is much less electron density that is in the living group, so that the nucleophile can easily attack, as compared, for example, when you have your iodide, no, or iodine in this in your substrate. So when the nucleophile attacks, and it is a very large atom here and very polarizable, no, it will have an effect on the nucleophile when it attacks. Okay, I hope that you get that. And therefore, the order of stabilization of the negative charge on the, let's say, transition state for the living group, no, it's much better for the living group in a protic solvent, no, if the living group is made up of fluorine, chloride, bromide, iodide, and it will become more stabilized in the presence of a protic solvent when you have fluoride, iodide, chloride, bromide, chloride, bromide, iodide. Okay. So other weak bases that are good living groups. So I have to emphasize here, good living groups. Good living groups, best living groups are the one that is stable an ion or a neutral molecule. Okay, so other weak bases that are good living groups. Weak bases are always good living groups. So other than the one that's being mentioned, you have your alkane sulfonate ions, alkyl sulfates. No, see how you see S double bond O can easily be stabilized here, and you have your alkyl toluene sulfonate. There are very, very weak bases, and be a very weak base. They are good living groups. Okay, and they're very, very weak base, and there are conjugate base of a very strong acids actually. So you just have to familiarize with these alkane sulfonate ions, and you can change on the SOO, no SOO, you can change with R, you can change with OR, you can change to this methyl group, toluene group here. Okay, so the trimethyl sulfonate ion, we changed this one with the R is CF3, this trimethyl sulfonate or triflate ions. It's a super good living group, no, by virtue of a very electronegative atoms here. And it's the best living groups known to chemists. It is the conjugate base of CF3SO3 and exceedingly strong acid with a pK of -5 to 6. So anyway, just have to familiarize with this. What would make it a good living group? No, because it contains 3 electronegative oxygen atoms. No, when it leaves, when it's connected to carbon, it has more tendency to draw the electrons. We can say, but it can be stabilized now by this system here. Double bond here. There is this resonance formation, no, when it leaves the substrate because of this sulfur double bond of sulfur. There is always this resonance formation, especially when there is how do you say this one? There is this system here, the benzene ring. It will also help form resonance structures. And the most stable, the most good living group is the CF3. And the CF3, there is a negative charge here, no? And there is this fluorine here. Fluorine is also an electronegative atom and can help disperse the negative charge by electron withdrawing inductive effect. So I have to say that the fluorine here will draw the electrons itself by inducing or induce niya by virtue of it having electron withdrawing effect. So it will induce and withdraw the electron density, that is the developed negative charge here, by inducing withdrawing the electron density on the neighboring atoms. It draws the electron density paingon sa iyaha that the negative charge on the oxygen will be dispersed. And that's what makes it more stable and a more stable weak base. And being a weak base becomes a good living group. Okay, so paman is this. So strongly basic ions really act as a living group. So whenever you have a very basic ion, it rarely acts as a living group. For example, the OH, no, it's a very strong base. It rarely leaves the substrate, no. The only reason that the OH can leave the substrate, no, so you see here there is an X. it doesn't live actually to form OH and the nucleophile attacking this. The only way that the OH can live is that first when it lives as a neutral molecule. There is no way that OH can exist, can live, no, because this is a strong base. It readily reacts, no, it is not stable. It is hard to stabilize the OH here. And so therefore it cannot easily leave the R here. So this is a strongly basic OH. Now it doesn't leave the ROH so easily. The only reason that the OH, the only way rather that the OH can leave the substrate is when the OH is protonated. Okay, it's protonated. So i-acidifies siya gamay such that the oxygen will react with the proton to form 3 bonds and positive. So once it becomes positive, the OH here becomes positive, then it can easily leave the substrate to form water. And that's the early one mentioned. It becomes now a good living group when it's being protonated, because when it leaves, it forms a neutral molecule, water here. And it's easy for the nucleophile to attack now the substrate. So there is a big difference when OH, being a strong base, can easily leave the substrate unless it's being protonated. No, so this is the statement here that strong basic ions rarely act as a leaving group. What else? So very possible. So here you have a nucleophile. So this very powerful bases such as hydride and alkanides. Virtually never act as a living group. Again, if the base is a very strong base, so saan ito pagkabalo pag strong base siya? Usually when you look at, there is an electron pair, and when it is, there is no way, when you look at the structure, there is no way that the negative charge can be dispersed or stabilized, then it will make it more strong base ion. Okay, so for example, hydride, no, there is no way that the negative charge in the hydride ion can be stabilized. That's why it's a very, very powerful, strong base. It always sticks with it positive center or a Lewis acid that it can donate its hydride, its alkyl density, also the alkali, the R minus. So therefore, reactions such as hydride leaving, for example, alkanol, it's not possible. It doesn't happen. These are not good living groups. Or naman siguro to. And then practice 6.18, and we go for the summary. In summary, no, SN1 SN2 reaction, I hope we still have time. For SN1 reactions, the following conditions favors the SN1 reaction. A substrate that can form a relatively stable carbocation ion, such as substrate with the living group at the tertiary position, favors SN1. Katong 3 degree carbocation, 3 degree alkyl groups, no, it favors SN1 reactions. When the substrate has or when we use a relatively weak nucleophile and weak nucleophile, or when we have a polar protic solvent. Okay, so in the SN1 mechanism, therefore is important in solvolysis reactions. And SN2, okay, you have a substrate. It favors the methyl 1 degree and 2 degree. We use strong nucleophile. We use high concentration of nucleophile, and we use protic, a polar aprotic solvent. So like your SN1, SN2. So the trend in the reaction rate for halogen is the living group is the same as SN1 and SN2. So there is the trend of the living groups, regardless of being SN1 or it being as SN2. Because alkyl fluorides RF react so slowly, they are seldom used in nucleophilic substitution. So we don't use the RF. No, we don't use the fluoride as a living group. Okay, that's it. And so this is the summary of SN1 and the SN2 reaction, the substrate, the